Every time you board a commercial aircraft, the plane climbs to a cruising altitude of somewhere between 9,000 and 12,000 meters and stays there for the duration of the flight. If you have ever looked out the window at that altitude and seen the curvature of the Earth, the absolute blackness of the sky above, and the thin blue line of atmosphere separating you from space, you may have wondered why the plane does not simply climb higher. Higher altitude means thinner air, which means less drag, which means less fuel burned per kilometer traveled. The logic seems obvious. If flying at 10,000 meters is efficient, flying at 15,000 meters should be even more efficient. Flying at 20,000 meters should be more efficient still. And yet every commercial aircraft in the world flies within the same narrow band of altitude. No passenger jet flies significantly above 12,500 meters. This is not a coincidence. It is not a regulatory limit imposed by air traffic controllers. It is a physical boundary defined by the atmosphere itself, and crossing it would destroy the aircraft in ways that most passengers never think about. Today, we will analyze exactly why that ceiling exists, what happens to an aircraft that approaches it, and why the engineering solutions that allow planes to fly at the edge of the survivable atmosphere are more sophisticated than most people realize.
To understand the problem, we need to understand what an aircraft actually does when it flies. A plane stays in the air because its wings generate lift. Lift is a force created by the difference in air pressure between the upper and lower surfaces of the wing. Air moving over the curved upper surface of the wing travels faster than air moving under the flat lower surface. Faster moving air creates lower pressure. The higher pressure beneath the wing pushes upward, generating the lift that keeps the aircraft airborne. This mechanism depends entirely on one thing. There must be enough air molecules around the wing to create a meaningful pressure difference. As altitude increases, the atmosphere becomes progressively thinner. There are fewer air molecules per cubic meter. The pressure difference that the wing can generate decreases. To maintain the same amount of lift at higher altitude, the aircraft must either fly faster, which burns more fuel and creates more structural stress, or increase the angle of attack of the wings, meaning tilt them more steeply into the airflow. Both of these options have hard limits defined by physics.
The angle of attack limit is called the stall angle. Every wing has a maximum angle at which it can be tilted before the smooth airflow over its upper surface breaks down completely into chaotic turbulence. When this happens, lift disappears almost instantly. The aircraft stalls. At low altitude, a stall is serious, but survivable if the pilots have enough altitude to recover. At 12,000 meters, with the wing already tilted near its stall angle just to maintain level flight, there is no margin for error, and almost no altitude to recover in. The aircraft is flying at what engineers call the Coffin Corner. This is not a metaphor. It is the actual term used in aviation engineering for the narrow speed range at high altitude where the aircraft must fly fast enough to generate lift, but slow enough to avoid tearing itself apart from the aerodynamic forces of high-speed flight. At the Coffin Corner, these two limits converge. The minimum speed needed to generate lift equals the maximum speed the structure can survive. There is zero margin between them.
The speed limit at high altitude comes from a phenomenon called Mach buffet. As an aircraft approaches the speed of sound, which is approximately 1,235 kilometers per hour at sea level, but decreases with altitude to around 1,062 kilometers per hour at 12,000 meters, the airflow over the wings begins to reach supersonic speeds locally, even though the aircraft itself is still subsonic. These local supersonic zones create shock waves on the wing surface that cause severe vibration, loss of control effectiveness, and potentially catastrophic structural damage. Commercial aircraft are designed to cruise well below this limit, at around Mach 0.85, which provides a comfortable safety margin. But as altitude increases, the speed of sound decreases, while the minimum speed needed for lift stays roughly the same or increases. The safety margin between the two limits shrinks. Above approximately 12,500 meters for most commercial jets, the Coffin Corner closes completely. There is no speed at which the aircraft can fly safely.
The engine problem compounds everything else. Jet engines work by compressing incoming air, mixing it with fuel, igniting the mixture, and expelling the hot exhaust gases backward to generate thrust. At sea level, a modern turbofan engine can process hundreds of kilograms of air per second. At 12,000 meters, where the air density is roughly 1/4 of sea level density, the same engine processes proportionally less air. It generates less thrust. It burns fuel less efficiently. The engine must work harder to produce the same thrust, which means higher temperatures inside the combustion chamber, which accelerates wear on the turbine blades. Turbine blades operating at the temperatures required for high-altitude flight are already working at the absolute limit of what modern metallurgy can achieve. They are cooled internally by air channels flowing through the blade material itself. The cooling air is taken from the compressor stages of the engine, which reduces the overall efficiency of the engine further. At altitudes significantly above 12,000 meters, this entire balance breaks down. The engines cannot generate enough thrust to maintain speed, and without speed, the wings cannot generate enough lift to maintain altitude.
There is also the pressurization problem. The cabin of a commercial aircraft is pressurized to simulate an altitude of approximately 2,400 meters, even when the aircraft is flying at 12,000 meters. This means the pressure inside the cabin is much higher than the pressure outside. The fuselage is essentially a pressure vessel, a hollow tube that must contain a pressure difference of roughly 0.6 atmospheres without failing. Every time the aircraft climbs and descends, the fuselage expands and contracts slightly as the pressure differential changes. This repeated pressurization and depressurization cycle causes fatigue in the aluminum skin of the fuselage. Engineers designed commercial aircraft for a specific number of pressurization cycles, typically tens of thousands over the aircraft's operational life. Flying at higher altitudes would require maintaining a higher pressure differential between cabin and outside atmosphere, which would accelerate fatigue damage and require either much thicker and heavier fuselage structures or much more frequent replacement of the airframe.
The Concorde supersonic passenger aircraft flew at altitudes of up to 18,000 meters and cruise speeds of Mach 2. It solved the Coffin Corner problem by flying through it at supersonic speed, essentially skipping past the dangerous transition zone by accelerating rapidly through it. But the solutions required to make this possible, a fuselage made of titanium instead of aluminum to withstand aerodynamic heating, engines consuming 4 times the fuel of a comparable subsonic aircraft, a passenger cabin with tiny windows to reduce structural complexity, made the aircraft economically unviable for anything except premium long-haul routes. Concorde required 25 years of development and billions in government subsidies before its first passenger flight, and it was retired in 2003 not because of technical failure, but because the economics of supersonic flight at that altitude could not be made to work at any ticket price the market would accept.
Modern commercial aviation has therefore settled on the current cruising altitude band as the optimal compromise between aerodynamic efficiency, engine performance, structural requirements, and passenger comfort. The atmosphere at 10,000 to 12,000 meters is thin enough to reduce drag significantly compared to lower altitudes, dense enough for engines to function efficiently, and at a pressure differential manageable by aluminum airframe structures. Every component of a modern aircraft, from the wing profile to the engine bypass ratio to the fuselage thickness, has been optimized for this specific altitude range. Moving significantly outside it would require redesigning everything from scratch, with materials and technologies that either do not yet exist at commercial scale or are too expensive for routine passenger aviation. The ceiling isn't where it is because no one has tried to go higher. It is where it is because the physics of the atmosphere, the limitations of materials, and the requirements of safe flight all converge at exactly that point. If this kind of analysis interests you, subscribe. What comes next will be even more interesting.